Thank you. Good afternoon. First, I want to thank workshop organizers for giving opportunity to give a talk. My talk on graphene-based hybrid films for transparent conductive film applications. So, sorry, it's just the content of my presentation. The first, some slides about transparent conductive films. Then we go to graphene and graphene metal nanowire hybrid films. So this slide shows some of many devices where the transparent conductive films are used. And mostly the large area transparent conductive films are used for various displays and touch panels and also solar cells. So about 90 or even higher, 90% of the TCF marks today use ITO as a transparent conductive film. And so the ITO with about 30 ohm per square and sheet resistance and transmittance about 90% is now commercially available and is used in different devices. However, today it is clear that emerging technology and the new devices needs no transparent conductive films, so new alternatives are being investigated to replace ITO. These are conductive polymers, carbon nanotubes, metal nanowires, and graphene. So among these alternatives, metal nanowires and graphene is the most promising because of the, first of all, the TCF characteristics that are comparable with that of ITO, or even this one even is better than ITO. And moreover, the metal nanowires and graphene can be used for flexible electronics or stretchable electronics that where ITO cannot be used. This is about graphene optical and electrical properties. You know this, that yesterday was also shown. So the monolayer graphene absorbs about 2.3% of visible light. So it's very high optical transmittance can be obtained about higher than 97%. Another feature is the graphene is a very high electrical conductivity. So the if you do a combination of the optical properties with electrical conductivity characteristics that demonstrate the graphene is a promising material for transparent conductive film applications. However, if we want to, when we want to fabricate transparent conductive films for practical applications, we need to address several issues. First of all, this is a fabrication. So now, today, there is more than 10 methods of 10 different methods of production of graphene. In this slide, I showed 4 of them. So first 2, this is micromechanical exfoliation of graphene and the high temperature sublimation of silicon carbide. This gives very high quality graphene, but the problem with this one is that they cannot produce large quantity graphene. Another 2 different methods are the CVD grown graphene on metal surface that was first developed by our group, by Roaf Group at UT Austin. And another one is a wet chemistry method, wet chemistry method that produces not exactly graphene, but is graphene and chemically modified graphene or graphene oxide. So we worked mainly on two types of graphene. One is a CVD grown graphene, another one is the graphene oxide. So if you see the pristine graphene with no defects on silicon oxide surface may have sheet resistance as low as about 30 ohm per square. But if you use the CVD ground graphene, if you fabricate transparent conductive films, the sheet resistance of the CVD ground graphene is about 1 kilo ohm per square. It's much higher than the pristine graphene. The reason of such high sheet resistance is because of the different type of defects that presenting in the CVD ground graphene. First of all, that is the graphene. CVD ground graphene is a polycrystal, has a polycrystal structure. It means the graphene domain is with the average size about 10-15 micrometer, and there's a submonolayer graphene. If you grow and you can obtain the continuous CVD ground graphene, where the graphene domains can form the grain boundaries between each other. And it was theoretically demonstrated, depending on the atomic structure, this grain boundaries can be transparent for charge transfer, while it may also be create a barrier for charge transfer. So this kind of grain boundaries is today is unavoidable, and we need to address when you are going to fabricate CVD ground graphene for TCF applications. Another type of defects are the other type of line defects. This is a CVD ground graphene on a copper foil, original copper foil. So first of all, if you see here is the black line is there wrinkles on a graphene on a copper foil. This arises due to the different thermal expansion of the graphene and the copper substrate. So this is this kind of wrinkles forms during the growth process, and if when you transfer this from the copper foil onto the target substrate, this kind of defects can be maintained. So you cannot remove this kind of line defects. Moreover, the copper substrate is not perfectly flat. If you see that the different grains of a copper has different roughness, and graphene during the CVD growth process conforms the surface roughness of the copper foil. So when you transfer this kind of graphene from this kind of copper substrate, you may obtain graphene on a silicon or on a glass substrate. You may obtain very different other line defects. So the transfer process produces other line defects that it is unavoidable today in CVD ground graphene. Here also this square shows some second layer of graphene, but there are very few. So our films are mainly on the monolayer graphene. So how we can decrease the effect of line defects on sheet resistance of graphene? One way is demonstrated by the South Korean research group. They showed just assembling one layer of graphene with other layer of graphene. So by putting four graphene layers, they obtained a sheet resistance 30 ohm per square with 90% optical transmittance. That is similar to the ITO film. And this group has used nitric acid in order to dope the graphene, but the problem here is the nitric acid is not stable, so the sheet resistance may increase about 50% within few days. Another approach was proposed by the Rice University group, the transferred graphene on top of the metal grids produced by lithography technique, and improved the electrical conductivity. So the sheet resistance is lower even this case. So here is single layer graphene, but the electrical conductivity here is mainly comes from the metal grid rather than graphene. So it was recent publications on Nature on Nanoletters that showed the integration of graphene, polycrystalline graphene, with one-dimensional nanostructures is a promising approach to decrease the effect of line defects like graphene grain boundaries. Because when do you put the nanowires or carbon nanotubes, you can cross the line defects and can breach the different graphene domains, and by this way you can eliminate or decrease the effect of line defects. So the showed that by this way one can obtain sheet resistance lower than 10 ampere square. So following this idea, we experimentally obtained the graphene silver nanowire hybrid films. In this case, our hybrid films, silver nanowire films are not globally, is not percolated. So they have no global electrical conductivity, but they can increase the electrical conductivity of graphene just locally. So what we did, we transferred CVD grown graphene on top of the silver nanowires, and this is the ACM images of the hybrid film. If you see here, there is one single nanowire crossing several line defects, and in this configuration, it connects this graphene domain with this with this one, so eliminating all this the effect of this line defects in the electrical conductivity properties. By assembling these two nanostructures, we obtained 64 ampere square with a 93% of optical transmittance. And by using another layer of graphene, so we did a two-layer graphene, we obtained sheet resistance about 20 ampere square with sheet resistance with optical transmittance about 91%. This is the highest value for the graphene nanowire, non-percolated nanowire system. And we tested our the graphene nanowire hybrid films to replace ITO. And here this is I do not go to details of the device fabrication you can find on this paper. So we just replaced one ITO film with our graphene silver nanowire hybrid films, and we used the electrochromic material, tungsten oxide electrochromic material that can be bleached or colored, reversibly bleached or colored. So this is our device that shows very nice coloration, very homogeneous coloration of the electrochromic material. So this one is the bottom electrode was graphene silver nanowire, while the top was ITO film. So this demonstrated that our hybrid films can replace the ITO for electrochromic device applications. So another type of graphene we used is produced by wet chemistry methods. This is completely different from CVD ground graphene, and the most attractive feature of this fabrication is a low cost. So you do not need any vacuum or high temperature furnace. So to produce the graphene oxide, the starting material is a graphite powder that the aged graphite powder has the grain composed of the layered structure of graphene, and by chemical treatment, we can obtain we can exfoliate graphene layers, and we can obtain highly dispersible graphene oxide. This is even dispersible in water, because our graphene now is not actual graphene, but it is graphene oxide. It contains a lot of functional groups assembled to this individual graphene platelets. The graphene oxide itself is not conductive. It's a very high sheet resistance. In order to for transparent conductive applications, we need to reduce graphene oxide. We need to remove the oxygen-containing functional groups, and we can obtain by this way reduced graphene oxide and significantly decrease the sheet resistance of the reduced graphene oxide. Today, there are many different methods of reduction of graphene oxide, so all can be classified into two different kinds. One is a thermal reduction, another one is a chemical reduction. We also recently developed a method in which we just simply deposited graphene oxide from the solution on top of aluminum foil, and we put this in a hydrochloric acid solution. Hydrochloric acid etches the aluminum foil. At the same time, they produce hydrogen that can react with the graphene oxide and efficiently reduce it. So we can obtain the reduced graphene oxide that is suspended, that is supported by PMMA layer, and you can transfer this kind of reduced graphene oxide on any type of target substrate. So the reduced graphene oxide films, you can, by simple method, by spin coating, dip coating, or the drop casting, you can obtain very smooth and continuous graphene oxide film. This is the reduced graphene oxide, reduced thermally on a quartz substrate. It's very transparent and very homogeneous film morphology. But the problem is that we have still very high sheet resistance, about 7.4 kilo ohm per square. So we tried different methods of the reduction, and there is today no method that can produce the reduced graphene oxide with a sheet resistance lower than 1 kilo ohm and with the optical transmittance higher than 90%. So reduced graphene oxide film itself cannot be used as a transparent conductive film. However, it is very good, very efficient in hybrid films, to fabricate the hybrid films. One is we tried the reduced graphene oxide integrated with metal nanowire films. So this is the SEM image of the silver nanowire films. The metal nanowire films are very low sheet resistance. It's better than ITO film. So TCF characteristics are better than ITO, but here is several disadvantages that limit the application of silver nanowire or even any kind of one-dimensional nanowire films. First of all, the electrical conductivity of nanowire films is provided by the percolated network of nanowires, while the optical transmitters are provided due to the open spaces between nanowires. So this kind of films has very low effective surface area because optically transparent area is not electrically conductive, and electrically conductive area is not optically transparent. If you use this kind of nanostructures as a transparent conductive film in solar cells, for example, the efficiency of the solar cell might be very low because of this kind of non-effective surface area. Another disadvantage of these nanowire films is a very high surface roughness and non-discontinuous film. Also, their poor adhesion, very low oxidation resistance that I will show in the next some slides. So what we did, we simply used the copper nanowire. This is also in the solution, and we used the graphene oxide solution. We deposited these two different films on two different substrates. Then the next step, we reduced the graphene oxide, obtained the reduced graphene oxide film. We delaminated of reduced graphene oxide and put again on top of the copper nanowire film. By this way, we obtained reduced graphene oxide copper nanowire film. The fabrication, okay, here is very some tricky stuff I think you can find on this, our recent publications. This is the SEM image of the reduced graphene oxide copper nanowire film. And this is the sheet resistance versus optical transmittance. The red dots show the only pure copper nanowire film. You see the sheet resistance of the copper nanowire, higher nanowires are higher than the hybrid film, copper nanowire coated with RGO film. So by this way, we obtained we significantly increased the copper nanowire film sheet resistance that initially was about 100 ohm per square. We obtained after assembling with RGO, we obtained about 27 ohm per square sheet resistance. This SEM images show some mechanism of the improving the electrical conductivity. First of all, the RGO covers all the surface area of the nanowire films. And if you see here, this kind of nanowires that you can always find when you do deposition of nanowire films, this kind of nanowires are not connected and they are not participating in percolated network. They are just contributing to the optical transmittance, decreasing the optical transmittance. So this is not efficient when you are using only nanowire film. But if you put the RGO, so these are not true, RGO can provide two-dimensional platform for charge carrier through the metal nanowires. Moreover, if you can see that this kind of nanowires can breach the platelets, graphene platelets, and decreasing the platelet junction resistance. Another feature is when you deposit the nanowire film, you can see many nanowires that are located very close to each other, but they are not contacted. Even very small gap between them have no electrical conductivity. So when you cover this kind of structure with a reduced graphene oxide, you can provide the two-dimensional conductive channel that can facilitate the transfer of the graphene, transfer of charge carriers through the nanowires and RGO. And this is another two nanowire films that initially was not contacted, so there is no electrical conductivity. After that we covered with the RGO film. They have we have electrical conduction through the two nanowires. So RGO, when it covers the nanowire film, it increases the electrical conductivity. But at the same time, in the meantime, that RGO can act as a protective layer from oxidation. The oxidation issue in metal nanowire films is very important. So if you see in this figure that this is a sheet resistance and changes by time. This blue one is a copper nanowire film. So you see that the sheet resistance increases by time. If you use higher temperatures, this increases more faster increase of the sheet resistance. But when we use the hybrid film, the nanowires coated with RGO, there is no significant changes in sheet resistance by this time range. So it demonstrates that RGO can protect the copper nanowire film from oxidation. Another one is also is a protective layer from degradation of copper nanowire films. So we used here we used reduced graphene oxide, copper nanowire hybrid films, and used as a transparent conductive electrode in electrochromic device. Prussian blue film was used as an electrochromic material, as an electrochromic layer. So the Prussian blue optical properties can be modulated by reversibly modulated from bleached state to colored state. So here we tried this kind of electrode. So this is half of the electrode is coated by reduced graphene oxide copper nanowire films. The another half of the electrode is only pure copper nanowire film. Then we deposited Prussian blue film on the top of this electrode. You see the homogeneous deposition of the Prussian blue film can be obtained. And next step, we try to use as an electrochromic device. So we try to bleach the film, the Prussian blue film. As you see, the Prussian blue only on the top of this area, only on the top of the hybrid film area, they are bleached. So this area works as a transparent electrode, but this area cannot work because here is pure copper nanowire film reacts very strongly reacts with Prussian blue and forms the copper iron cyanide complex that are the reaction of Prussian blue with copper nanowire completely destroy the copper nanowire and the percolated network of copper nanowires. So summarizing about our hybrid film, so this is a pure RGO single component film. The main disadvantage of the RGO film is a very high sheet resistance of the films. And pure metal nanowires, we have very good, very low sheet resistance, very good optical transmittance, but disadvantage is a high surface roughness, discontinuous film, and poor adhesion. So when we assemble these two single component films, we obtain the hybrid films where this kind of disadvantage can be minimized or can be completely eliminated. This is a summary all of my presentation. So we can use graphene, the two type of graphene developed by, produced by two different kind of fabrication method. One is a CVD ground graphene, another one is a reduced graphene oxide produced by wet chemistry methods. Next step, we can integrate this graphene with the metal nanowires, and we can obtain graphene nanowire or RGO nanowire films. So in this case, we can, in case of CVD graphene with nanowires, the CVD graphene is a main conductive film, is main conductive component in the hybrid film, while nanowires are just as an additional component to decrease the sheet resistance of the CVD ground graphene. And the RGO nanowire films, so RGO is, the nanowires are the main conductive, electrically conductive component, while RGO is an additional component that can efficiently increase the electrical conductivity, but also increase the performance in terms of oxidation resistance or the chemical and thermal stability of hybrid films. So this work was done at UT Austin, and there's several postdoc and PhD students from the Ruoff group were involved in this work, and our collaborators, the Professor Akinwande Barek from the UT, and the Professor Schwetz from UT Austin, and the UT Dallas, some collaborators from UT Dallas, and also some collaborators from Tokyo Electron. Financially, this work was supported by NSF project and the Semiconductor Research Corporation, as well as Tokyo Electron and senior short-term mobility research programs. Thank you very much.